Okay, so now let's talk about hyperbolic paraboloids. We had elliptic paraboloids, now we've got hyperbolic paraboloids. And these look like z over c is equal to x squared over a squared minus y squared over b squared. So the difference here is that instead of having a plus, we have a minus. So for example, let's sketch z equal to y squared over 9 minus x squared over 4. Yes, I swapped the directions that I had x and y here, but really imagine that I had -1 for c here and then multiply through by -1. We arrive at this. The reason I chose this is it's just slightly easier to sketch this sort of hyperbolic paraboloid just with the way that we typically draw our axes. Anyways, so we look at the traces. If we take x to be constant, we get z is equal to y squared over 9 minus k squared over 4. So that's a parabola in y and z. And it opens upward because y squared over 9, the coefficient is 1/9, is positive. So there's an example. Now the thing to notice is that as k increases or decreases away from 0, k squared over 4 gets bigger, so we're subtracting a bigger and bigger thing. So these parabolas will actually have vertices which are going further down in the z direction as we move away from the origin where the hyperboloid is or the paraboloid is sort of sitting in this case. When y is equal to k, we're taking the vertical slices in the y direction. We get z is equal to negative x squared over 4 plus k squared over 9. Because it's negative x squared over 4, this is a parabola that opens down. But as k increases or decreases away from 0, k squared over 9 gets bigger, so the vertices will actually go up in the z direction as we move away from the origin. So I've drawn two of these guys here, these vertical slices that are parallel to the xz plane. There's the one at the origin, and you see as we let y get bigger, this constant gets bigger, k squared over 9 gets bigger, we start, our parabola starts moving up. Okay, it's kind of hard to draw too many of these guys without really messing up the picture, so I just decided to draw this many. But the vertical slices are a lot different, but this is just like our elliptic paraboloid. With the elliptic paraboloid, our vertical slices were parabolas. Here they're still parabolas. In the elliptic case, they both opened up or both opened down. Here, one of the slices opens up, one of the cross-sections open down. So here we have the cross-sections in the x direction open up, cross-sections along y open down. And what happens in the horizontal direction, what happens as we cut up along z? Well, we get y squared over 9 is minus x squared over 4 is equal to k. This gives us either a hyperbola when k is non-zero. If k is less than 0, that is z is below the origin, then we got hyperbolas that open like this and this, imagining this is x and this is y. So we get these hyperbolas down here that sort of bend towards x. If k is greater than 0, that is we're above the origin, then we get hyperbolas that open like this, that is towards y. And if k is equal to 0, we get y squared over 9 minus x squared over 4. It turns out that is equal to 0. That is the equation of two lines. So that's this bit right here. That sort of third guy from the bottom or from the top is actually just two lines that go straight through the origin. And this is what it looks like. So our cross sections vertically or horizontally are pretty much hyperbolas, except for one is a pair of lines. The vertical ones are parabolas. They open up if we slice along x, they open down if we slice along y. Alright, just like with the elliptic paraboloid, there are really sort of two orientations of a hyperbolic paraboloid that depend upon whether c here is positive or negative. So let me actually start with this case here, c less than 0, because that's the case we already looked at. What happens here is that the paraboloid lies below the x-axis, but above the y-axis. Great, so that's what happens there, and we get this sort of picture here. In the other case, and you know, I seem to remember being really great at drawing these sorts of things back in college, but man, for some reason I found this super hard to draw, even though it's not too different from this, but this I found to be super hard to draw. Maybe you'll come up with a good way of drawing it. Anyways, when I have c greater than 0, it's like this is just flipped upside down, and so now it's above the x-axis, it's like sitting on the x-axis, but it's below the y-axis. So here's question 2, and this is just for good practice. Sketch the traces of this hyperbolic paraboloid that we were looking at. Z is equal to y squared over 9 minus x squared over 4. And why don't you choose the traces where x and y are equal to 0, plus or minus 1, plus or minus 2. You'll realize something, which is that some of these traces are the same. And then for z, just to make your life a little bit easier, how about for 0, plus or minus 1, and plus or minus 4? Put the plus or minus 4 here because it'll be a little bit easier to sketch the hyperbolas if you have a square here instead of a non-square. So just go ahead and try those out. All right, let's talk about this other, I suppose, class of quadric surfaces, and this is where x, y, and z all appear to the second power. And one possibility is we have something like this: x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. So, great. Note that if all of these things are positive on the left-hand side, so this is only going to have a trivial solution if we have a 0 on the right-hand side, which would be 0, 0, 0. That's not very interesting. And if the right-hand side were a negative number, then there'd be no solutions whatsoever. Positive plus positive plus positive must be positive. So it only makes sense to have a positive number on the right, and no matter what it is, we can divide through and make sure it's equal to 1, and just change the a, b, and c. In this case, we get something called an ellipsoid, which is really the proper three-dimensional generalization of an ellipse. And every single trace, no matter whether it's vertical or horizontal, over x, y, or z, it's an ellipse. So let's look at x squared plus y squared over 9 plus z squared over 4 is 1. If we set k, x equal to k, a constant, we have y squared over 9 plus z squared over 4 is 1 minus k squared, which is an ellipse in y and z. So I drew 1 here. Similarly, if y is a constant, we get an ellipse. I drew a bunch of different possibilities here for different values of k. And if z is equal to a k constant, we get horizontal ellipses in the xy plane. Great. Just like with regular ellipses, if we write it in this sort of format, we can always tell where sort of the extreme points along each axis are. The x-coordinate of the extreme points on the x-axis will have x-coordinate a and y-coordinate 0 and 0, or plus or minus a really. Along the y-axis, the y-intercepts will be plus or minus b. Those are extreme points along the y-axis. Along the z-axis, the extreme points have z-coordinate plus or minus c and x and y-coordinate 0. And so, for example, since we have a equal to 1 here, b equal to 3, and c equal to 2, we know that our ellipsoid will hit the points 1, 0, 0, and also on the other side, negative 1, 0, 0. Goes through 0, 3, 0 over here, and over here this is going to be 0, negative 3, 0. And up here it goes through 0, 0, 2. Down here it'll go through 0, 0, negative 2. So there is our ellipsoid. In particular, if a squared is equal to b squared is equal to c squared, then we end up with a sphere. We can multiply through by denominators. We get x squared plus y squared plus z squared is equal to r squared, where r is the radius of the sphere. Fantastic.